Our world is hungry for energy. We need it to power our homes, fuel our industries, and drive our transportation. As we seek cleaner and more sustainable energy sources, one option stands out: nuclear energy. Deep within the heart of atoms lies a reservoir of energy that dwarfs anything we can harness from fossil fuels. This energy, locked away in the atom's nucleus, is the key to understanding nuclear power. Fission occurs when the nucleus of a heavy atom, such as uranium, is struck by a neutron. This collision can cause the uranium atom to split into lighter atoms, releasing a tremendous amount of energy. By harnessing the power of nuclear fission, we can generate vast amounts of electricity without producing greenhouse gases. At the heart of every nuclear reactor lies the process of nuclear fission. Picture an atom as a miniature solar system with a dense nucleus at its center orbited by electrons. Certain heavy atoms, like uranium-235, are inherently unstable. Their nuclei are like delicate structures, easily disrupted by the slightest nudge. That nudge comes in the form of a neutron, a subatomic particle with no charge. When a neutron strikes a uranium-235 nucleus, the nucleus absorbs the neutron, becoming briefly unstable. This instability is short-lived, and the nucleus quickly splits apart, releasing an astonishing amount of energy. The energy released during fission takes various forms, including kinetic energy and gamma rays. It is this energy that we harness in nuclear reactors to generate electricity. Nuclear fission, while powerful, is not enough on its own to power a city. To generate a sustained and controllable release of energy, we need to initiate a chain reaction. Picture a single domino standing upright. If you topple it, it falls onto the next domino, creating a chain reaction. A nuclear chain reaction operates on a similar principle, but instead of dominoes, we have uranium atoms. When a uranium-235 atom undergoes fission, it releases energy and additional neutrons. These neutrons can collide with other uranium-235 atoms, causing them to fission as well. Nuclear reactors are designed to harness this chain reaction in a controlled and sustained manner. Nuclear reactors are marvels of engineering designed to control and harness the immense power of nuclear chain reactions. These intricate systems are the result of decades of research and development, combining physics, engineering, and safety protocols to create a reliable source of energy. Imagine a giant pressure cooker, its core filled with carefully arranged fuel rods containing uranium-235. These rods are the heart of the reactor, where the magic of nuclear fission takes place. These fuel rods are submerged in a pool of water or other coolant. This coolant is crucial as it not only cools the reactor but also plays a vital role in the fission process. The coolant acts as a moderator, slowing down the neutrons released during fission. By slowing these neutrons, the coolant ensures that the chain reaction remains steady and controlled. It also absorbs the heat generated by fission, preventing the reactor from overheating. This heat is then transferred away from the reactor core, maintaining a stable temperature. To control the rate of the chain reaction, reactors employ control rods, typically made of materials like boron or cadmium. These rods are inserted into the reactor core to absorb excess neutrons. By inserting or withdrawing these control rods, operators can regulate the reactor's power output. This precise control is essential for both safety and efficiency. The heat generated within the reactor core is then transferred to a separate loop of water, turning it into steam to drive turbines and generate electricity. This process is the final step in converting nuclear energy into a usable form, powering homes and industries. Fuel rods, the heart of a nuclear reactor, are not your typical fuel source. They are meticulously engineered assemblies designed to withstand the extreme conditions within a reactor core. Each fuel rod is a long, slender tube, typically made of a corrosion-resistant metal like zirconium alloy. Inside these tubes, pellets of enriched uranium fuel are stacked end to end. The term enriched refers to the fact that the uranium used in fuel rods contains a higher concentration of uranium-235. The precise level of enrichment varies depending on the reactor design. The fuel rods are then bundled together into fuel assemblies, which are loaded into the reactor core. Over time, the fuel rods lose their effectiveness and must be replaced, typically every few years. Controlling the nuclear chain reaction within a reactor is paramount to ensure safe and efficient operation. This process is akin to walking a tightrope, where precision and balance are crucial to avoid any mishaps. This delicate balancing act involves two key components: control rods and moderators. Each plays a vital role in maintaining the reactor's stability and efficiency. Control rods, often made of materials like boron or hafnium, are the brakes of the reactor. They are designed to absorb neutrons and regulate the fission process. These materials are chosen for their ability to absorb neutrons, effectively stifling the chain reaction. By doing so, they prevent the reactor from overheating and ensure a controlled release of energy. By inserting the control rods deeper into the reactor core, operators can absorb more neutrons, slowing down the rate of fission. This is crucial during periods of high reactivity when the reactor needs to be stabilized. Conversely, withdrawing the control rods allows more neutrons to interact with uranium-235 atoms, increasing the rate of fission. This adjustment is essential when more power output is required. Moderators, on the other hand, act as the reactor's accelerator. They play a different but equally important role in the fission process. They slow down neutrons, making them more likely to cause fission in uranium-235 atoms. This slowing down is essential for maintaining a steady and efficient chain reaction. Water is a common moderator, slowing down neutrons through collisions. Its abundance and effectiveness make it an ideal choice for many reactors. This slowing down increases the likelihood of fission, making the chain reaction more efficient. By carefully balancing the use of control rods and moderators, operators can ensure the reactor runs safely and efficiently, providing a reliable source of energy. The intense heat generated by nuclear fission within the reactor core is a marvel of modern engineering. This process involves splitting atomic nuclei, releasing a tremendous amount of energy. This energy is not an end in itself, but rather the means to an end electricity generation. The heat produced is harnessed to create the power that lights up our cities and fuels our industries. This transformation from heat to electricity follows a process similar to that of conventional power plants, where heat is used to produce steam that drives turbines. As the fission reaction proceeds within the reactor core, the coolant circulating around the fuel rods absorbs the heat. This coolant, often water, plays a crucial role in transferring the heat away from the reactor. This superheated coolant, typically water, is then pumped to a heat exchanger. The heat exchanger is a vital component that ensures the efficient transfer of heat from the reactor to the steam generation system. Within the heat exchanger, the superheated coolant transfers its heat to a separate loop of water, turning it into steam. This steam is what ultimately drives the turbines. This steam is then directed towards turbines, large rotating machines connected to generators. The turbines are designed to convert the thermal energy of the steam into mechanical energy. The high-pressure steam forces the turbine blades to spin, generating electricity. This mechanical energy is then converted into electrical energy by the generators. The electricity generated is then fed into the power grid, ready to power our homes and industries. This intricate process ensures a steady supply of electricity, highlighting the importance of nuclear power in our energy landscape. Nuclear power, while a potent and efficient energy source, comes with inherent risks that necessitate stringent safety measures. The potential consequences of a nuclear accident are severe, underscoring the need for unwavering vigilance. Nuclear reactors are designed with multiple layers of safety systems to prevent accidents and mitigate their impact. The reactor core is housed within a containment structure, a robust barrier typically made of thick steel and concrete. The control rods play a vital role in preventing runaway chain reactions, with backup systems in place for rapid insertion. Emergency cooling systems are designed to flood the reactor core with coolant in the event of overheating. Nuclear power plants are subject to stringent regulatory oversight to ensure safe operation. As we navigate the challenges of climate change, nuclear power stands as a beacon of hope, offering a path to a sustainable energy future. Its ability to generate vast amounts of electricity without emitting greenhouse gases makes it indispensable in our fight against global warming. However, challenges remain. The safe disposal of nuclear waste, the risk of nuclear proliferation, and the potential for accidents continue to fuel public concerns. Addressing these challenges through technological advancements and enhanced safety protocols is crucial. The future of nuclear energy is bright, with ongoing research focused on next-generation reactors. From small modular reactors to fusion power, the future of nuclear is ripe with possibilities. By harnessing the power of the atom responsibly, we can pave the way for a cleaner, brighter, and more sustainable world.